had this nightmare. I've actually had this nightmare where I'm in front of the class and I start talking and I'm like, I have no idea about any of it. And it's such a weird feeling, and so it's always, I know this, so I'm not gonna die doing this, but when you're teaching a class, I taught classes for like the first time, and I hadn't seen the material in 15 years, because that's when I last took the class, right? So a lot of you see a little bit of it, but not, so that summer I'll just like go through, because then that nightmare's in the back of my head. I'll get up here and today we'll talk about this, and I don't know, sure. But I've had professors too that start doing a problem and they get to a point like, oh, I'll do this later and give it to you. And you're like, wait a minute, dude. So I try not to do that either, but yeah, because that sucks.
No, but it was
can't do
really
what you
bad because we didn't have any other examples for that homework. It was because it was a minimum day, and then he assigned it anyway. He's like, you guys will
do it. Somebody's got to do it. I can't do it.
Somebody will figure it out.
So which one? Sorry, 4 or 5?
18.
So what's really important on these probability problems is when they give you numbers, you want to assign them symbols so you know what the hell you're talking about. So what I mean by that is 24.9% of robberies are cleared with arrests. So 24.9, so 0.249 is the probability of what? Give it a symbol.
R.
Okay, you could use R. I like it. So then we know that R means a robbery cleared with an arrest. And it kind of makes sense. It's actually higher than I would think. 25% of the cases are actually solved. Somebody's arrested. Are they the ones that did it? I don't know, but somebody's arrested. You with me? So that's number one, is when they give you a number like this, assign it a symbol so that you can use the formulas easier. Right here I can't count anything. They didn't give me 38 robberies and 2 of them were solved. They didn't give me something to count. I've got to use the formulas. A new detective is assigned 10 different robberies. What's the probability that at least one of them is cleared with an arrest? So that's part A.
None of them.
Now let me do this real quick. What would this be here?
None of them. You subtract from
Before we get to that question there, what would this be? What does that symbol there mean right there that I put over the R?
complement.
Complement, which is really another word for not. So this is robbery cleared with an arrest. This is the robbery was not cleared with an arrest. So what would that be by itself?
You subtract from the.
Yeah, 1 minus this.
What number are you doing again?
18, yeah. And this is section 4.5. Alright, so how are we doing so far? I mean, and you know this is a key step. Some of you know this from algebra. If you summarize what they tell you, like a word problem, you want to summarize what they tell you so you can do. Anytime you have a wordy problem, so obviously statistics, wordy problems, you want to summarize what the hell they tell you. And what I mean by that is translate into mathematics. Give us some symbols so you can start thinking about where to plug them into formulas. So what's probably at least one robbery cleared with an arrest? How many ways would there be one robbery? At least one. So maybe the first one was cleared and the other ones weren't. Or the second one was cleared and the other ones weren't. Or the third one. Or maybe the first 2. Or maybe the middle 7. Or maybe the last 3 and the middle 2 and the first. Holy crap. Right? I hope to God some of you understand. I've done that several times. I've done that whole, holy crap. I really desperately want you to understand what I mean when I do that. If I were to answer this question directly, thank God there's another way to do this. If I were to answer this question directly, I would have to figure out the probability of this plus the probability of this. So just make the R float. Is that cool? Because if one of them did, it could be the first one or the second one or the third one or maybe the 10th one. And then what's another way to be at least one? Maybe 2 of them, the first 2 and the middle and the next 2 and the next 2, or maybe the first one and the third one, or maybe the first one and the fourth one, or maybe the first one and the 5th. Holy frickin' shit. Right? You guys kind of with me now? You'd have to calculate all those probabilities and add them up. Because you could do it this way, or this way, or another way, or way too many ways, right? So what comes in or stays or as here? Yeah, probability of at least one
It's none of it.
is 1 minus probability of none. And that's not bad at all. So what's another way to say probably that none of them were cleared? I'm going to have how many of these? 10 of these. So the only way to do none cleared is each one was not cleared. 0.751 times 0.751 times the first one wasn't cleared, and what's and mean? Multiply. The second one wasn't cleared, and the third one. But what's a better way to write that? To the 10th power. And you get your 1 minus. Now I like this problem for a few different reasons. One, it hammers home this idea again, the at least one idea. What do you guys get for that probability?
I got 94%. That at least 1 year. Yeah.
So 94?
Yeah.
So you get like this is 6% or something like that? So 0.94?
9429, yeah.
Okay, cool. So the other thing is just getting used to rewriting these in the more compact form. If I have 10 of something, I can just write that to the 10th power. This one and that one and that one. How are we doing so far? Is that decent? So what about part B? What's probably that the detective clears all 10 robberies? Now this is not an at least one. How many ways is there for him to clear all 10? Was one way. Somebody grab the door for me. Thanks, man. There's just one way to do it, so I don't go through this whole list of holy crap, right? I just do it the one way. What's the one way they can all be cleared? Yeah, how many whats do I want? If I want them all cleared, the probability all cleared, that would be R 10 R's in a row, right?
Yeah.
And each R, of course, and another way to write R times R times R times R is R to the 10th power. And what is R?
0.2.
Yeah, 0.249
For about 10.
to the 10th. And that's going to be, some of you guys hopefully can realize that's going to be crazy small. And it really should make sense. If there's only a 25% chance you're going to clear one, what's the chances you're going to clear 10 of them? Very small, right? It's always nice when math goes along with our gut. A lot probably doesn't, but this does. What do you get when you do? Some of you guys might get something you can't interpret.
Yeah.
It's 9.16 e to the 7th, e to the negative.
9 point who what?
16.
E
To the negative 7.
E negative 7, and that E means times 10 to the. Remember good old times 10 to the? Scientific notation. So that's the way the calculator displays something that's going to be stupid small. It just says screw all the zeros. Let me just give you the shortcut. All right. How do I rewrite that as a decimal if I really wanted to?
Will be next. 9.6.
Good. There's always one less zero than the power, because it's got to go back 7. It's got to go once around the 9, and then the rest are zeros. So it's going to be 1, 2, 3, 4, 5, 6. So that is the probability. That's not even the, percentage. You move the decimal over a couple times, that's the percentage. So that goes along with our gut. It should be really close to impossible to clear all 10. And then this part, I love part C. Now here's where part C is really good. This is getting us looking ahead towards chapter 8 even, where we prove something. Part C says, what should we conclude if the detective actually does this?
He's a genius.
Yeah, either he's a genius.
Or the robberies were fairly obvious. That's the other option.
Okay, or they were really obvious. Like every single one of them, he stops and holds up his ID for the camera. Good luck finding me. Oh, so I should. All right, so that could be true.
He might be making false clears.
He might be making false clears. Yeah, he might even be planting evidence. You never know. So it could be either he's a crazy genius, Sherlock Holmes type, person, or he's planting evidence, or he's involved somehow. He's just rat these guys out, and his life is numbered anyway.
Can we say that the results are unusual?
Certainly.
Yeah.
But I want you to go further.
Okay.
Interpret it in terms of what you would think if you were his boss. What would you think? You think, holy crap, you're really smart, or what the hell's going on here? That is evidence. That would be evidence that something weird at least is going on. You with me? That is such a small number, such a small chance that it would randomly happen, that there must be something special here. Either he's a genius or he's involved somehow. Right? Anybody ever watch Monk?
Yeah.
I love that show. I remember that show. There's one time the guy was solving things better than Monk was, and it was because he was actually involved in it somehow, so that's what I'm thinking about. All right. I miss Monk. That problem is a perfect microcosm of my preferred type of problem, just to give you a big insight. It takes you through all the steps here. At least problem, a straight up just calculate the probability problem, and then an interpretation question. Can you interpret what the hell you just saw? Right? That's the big key. A lot of people in math just want to give me that number. Statistics, you got to tell me what the hell it means. That's the whole point. Any other questions from homework? You're doing okay. Cool. Yeah.
Give me 24 on section 4.1.
4.4.24. Oh, good. All right. This one has got something that I would allow for, because it's got one little piece to it that's not obvious. But this is another one. Well, there's a lot of problems here I love, actually. So you just got to get used to me saying that. Number 24 is definitely one. So if you haven't looked at this yet, read through that. It's page 169. Okay. So you guys get the idea? I mean, obviously, the more people identify somebody as the person that did something, that's more evidence that they did something. You with me? You know, that's why you have lineups and multiple witnesses help and all that kind of thing. So let's break this down. There's 9 different people that are choosing from 5 different men, right? That's the idea. And sometimes we get a little confused about 9 and 5, what is where. So think about it like this. If one of the 9 people that are choosing, there's 5 people to choose from, right? You can't change that. What's the probability that any individual person would pick a certain man? So you got 5 men.
You will divide by 5.
You got 5 men sitting up there. What's the probability they all pick one of them? Say number 4.
4 over 5.
Don't think like that.
1 over 5.
Not 4.
1 over 5.
1 out of 5. Good. So the probability that any individual would pick the same man, would pick a certain man. There's just no way to say this quicker. It's 1 out of 5. And a related kind of problem would be in a multiple choice test. If every question had 5 possible answers and there were 9 questions, what's probably you guess correctly on any given problem? 1 out of 5. There's just a 1 correct answer out of 5 possible. So then what's probably you guess correctly and get 100, 1 out of 5 times 1 out of 5 times 1 out of 5, because you have to guess the first one right and the second one right and the third one right. Are you guys kind of with me? So it's very similar to that problem. There's one little difference though. So if you were to say, let me see who was listening, because I basically almost just gave you the answer here. If I got 9 people now that have to do this, and I want them all to guess the same person. Not to guess, but to pick. So I want the probability that all of them pick the same man. So the first one picks a dude, and the second one picks the same dude, and the third one picks the same dude. Does that feel like what we've been doing this whole time? The first one does this, and the second one does and so it's a bunch of multiplications. So if you did this, somebody might know the twist here, but every single one is 1/5, right?
Yeah.
And if you said because there's 9 of them, I'm going to have 9 1/5s, I would understand why you made that mistake. That is a mistake. And it's almost unfortunate. The key is this, and I don't want to get us bogged down in this because it doesn't happen all the time. Are you guys with me? Does that make sense? We got 9 dudes. It's a 1/5 chance each one of them picks a dude. So it should be 1/5 to the 9th. Why are you making this all confusing, Jeff? Just shut up and leave it at that. I can't. To pick the same dude, somebody had to pick a dude to start with. The first guy picked somebody. What's the chance that he picks somebody? 1. So he has to get them started. The first guy could pick any of the 5. And then the rest of them pick that same dude. You with me? A little bit? Now, if you don't quite understand what I'm saying, I understand there's one little evil piece to this problem. If you do 1/5 to the 9th, I would leave you alone. I'd be happy with it. But I really want you to understand, the first guy's got to pick somebody first, and then everybody else agrees with him. Yes, sir?
But wouldn't him picking number 4 first, wouldn't that still be a 1/5 chance picking him?
Yeah, but who could he pick? 5 out of 5. He could pick any 5 out of the 5
Yeah, so if
to
you
get it started.
It's probability of pick a certain person, not probability of picking number 4.
Exactly. So if it was 4,
Yeah.
there's a 1/5 chance, but it could have been 5, or it could have been 3, or it could have been 2, or it could have been 1. Add them all together, that's 1.
Because there's a 100% chance he's going to pick something.
Somebody, just to get them started. Yeah.
So another way you could put it is that 1 is actually 5 out of 5.
5 out of 5.
There's a 5 out of 5 chance that he will pick.
Because he gets to
any
pick.
one.
What's probably he's the same as the person that came before him. Nobody came before him. So he's got a 5 out of 5 chance of being the same as himself. Everybody else has a 1 out of 5 chance of being the same as him. There you go. That's the right way to say that. That's good. I got a few more agreements, and I got some people going, move on. All right. But if you did 1/5 to the 9th and you don't understand what the hell I'm babbling about, I understand, and that's close enough for me because that little twist is actually kind of evil. It actually makes this problem a little harder than it really should be. But it's an interesting thing. And there's an old, not a joke really, but there were 4 students who came late to a test, and they said, it was like final exam. And they said, oh, dude, can you let us start? We had a flat tire. He said, all right, well, you guys meet me one at a time in my office. And so what he did was he asked them, forget it, story time. Great, I'm showing my age. So he gave them each like a piece of paper, and he said, okay, here's your one question. Here's the one question. Which tire went flat? Right? So the probability, if they were just making up a story, then the probability that they happen to guess the same tire would be pretty small. Right? In fact, we can figure it out. The first guy picks a tire, and the next 3 pick the same tire. And he wasn't driving a semi or something, it was just 4-wheelers. You guys with me? And that's decently small for the professor to feel like, well, this is going to be evidence if you guys pick different tires, or if any of you pick a different tire, screw it, you're lying to me. You don't get to take the test. Right? It's the same exact situation. Okay. Is that, where are we at, 18?
Yeah, were they telling the truth? Is that they don't find out?
That's statistics, you don't know. Now you know how it feels to be a statistician. You got evidence, but you don't know for sure. Which one was this again, 24? Oh, does this constitute, does anybody do this for me? What's 1/5 to the 8th?
5 0 2 5 6. 0 0 0 0 0 2 5 6.
256?
Yeah. 5
What you
zeros
got?
in front of it.
And you got 2.56?
2.56 times 10 to the -6.
I like it. So 1, 2, 3, 4, 5.
1, 4.
Is that small enough? Now, if they do all pick the same guy, is that small enough to be evidence? I mean, it's such a small chance that was going to happen randomly that what's more likely? That guy did it. You with me? Okay. Does that constitute reasonable doubt? No, that would be unreasonable doubt. If you doubt them because you go, there's still a chance that my client did not do it, and the jury, you guys did it. Give me a break. He's right, there is still a chance his guy didn't do it, but it's so damn small that what's more likely is he did it. Next case.
The only thing is the given is already that it was by random guesses.
No, that was if it was by random guesses.
Yeah, you always, so let me take a step back. There's a problem with,
But that would be your reasonable doubt, because you know they guessed randomly.
Exactly. So you know that happened, so there's a problem, where they have couples wanting a girl, so they do this special technique, and then there were like 600 girls and 70 boys, or whatever the hell it was. I don't know if you've done that problem yet or not. But what number would you compare that to? If there were 600 girls born and 70 boys born, bless you. What percentage of girls came out of that? 600 over 670, right? What would you compare that to tell if that was effective? What's the normal?
50.
50, there you go. See, so that if it was done randomly, that's what you compare it to. And you say, so does it look like it was done randomly? No. Because the probability that it would happen if it was done randomly is so small that what's more likely, it wasn't random. It actually is that guy. He's guilty. Or they all know him and hate him.
Oh, that makes sense.
Going to jail. Or something, do you understand? I shouldn't joke too much because then it makes it more confusing. Okay. So there's always going to be this, I want to compare it to what would happen just randomly. Just what would happen, and then if that probability is really small, then it was probably something not random. It was, they're connected. They picked that guy because he did it in this case. Right? Or if they all picked the same tire, then they probably were telling the truth. That's evidence they were telling the truth. Because it's so small that it would happen otherwise. Okay. Charlie Hopeful. Is there anything else from chapter 4?
17.
17.
4.4.
4.4?
Yeah. Page 169.
Alright, so this will be the last one we'll do here. This one has a little table, and it says, this is 17 and 4.4.
We didn't have to do that.
That's all right. If 2 of the 100 subjects are randomly selected, so if 2 selected, we'll do it together real quick. Find the probability that they are both group O and type Rh positive. And this is with and without replacement. So you have 2. So there, my little hangman game is going to have 2 spots for probabilities. So the first one I pick is picking 2. So I pick the first one. This is the probability that they're O and Rh positive. Looking at the data. Thankfully, it's all out of 100 here, right? It's always nice when they do that. So O and Rh positive. How many people are like that?
Oh, 39.
39. I love it. So and since it's out of 100, that would be 0.39. Let me do that out of 100, just to make it quick. I put that person back in. I don't put them in the next room or something. What's probably that the next person I pick is O and Rh positive.
39 out of 100.
It doesn't change because I put that first person back in. Right? And then whatever that is that cool? So the first person had a 39 out of 100 chance of being O and Rh positive. I put him back in the room. So all the probabilities are the same. So, and the second person is O and Rh positive, the same probability. The key difference between part A and B is, what if I do the first dude and put him somewhere else? Now what's probably the next person is this.
30.
Yeah, there's one less O and Rh positive out of one less person.
Yeah, but the question isn't it that O is 39 over 100 and RH is 86 over 100.
No, come on now, come on.
Why?
O and Rh positive is one situation. One situation. I want 2 people that are O and Rh positive. So how many people are O and Rh positive? 39.
I think he was thinking O or Rh positive.
Yeah, because how many people are O by itself? 45. Right?
Yeah.
But this defines O and Rh positive people, so that must be 39 people do both out of 100. So that's the first person right there. That's person 1 being O and Rh positive. And I want person 2 to be O and Rh positive. So these two are in here. They're part of that already.
Two events.
Yeah, no given. There's no given. So that's why they're both out of 100. Cool. This one, there's sort of a given. This one says, given that I already picked somebody, this probability changes a little bit. They lose a person. Okay. All right. So let's get back into 5. And let me see. I got 2 things. I have a little bit to tell you about standard deviation. Then I'm going to let you guys work on a handout. And then I've got another handout printing out in my office right now to go along with section 5.3 and 5.4. So somebody remind me, let's do a real quick little review problem. And there was a really good question at the end of class. I must give you, the problem has to give you both of these together. Because that's my complete data set. If I just say 1, 2, 3, 6, 9, that's not my complete data set. You didn't tell me what percentage were 1, what percentage were 2s. You with me? Okay, so then I also give you this. So this is not something I calculate somehow. So let's say this is, oh, can I make up something this data represents? I don't know, the
States visited a lot.
I like states visited in the last year. Thank you for that. So let's say, it's probably going to be a big chunk here. A lot of people don't really have to go anywhere too much. We got a big ass state we live in, so we can go very far and still be in one state. So, so let's say 2, let's say 21, 3, what do I got so far? Okay. Let's make them 09, 6, 03, and 9, 02. Does that add up correctly? Looks like it might. Yes, cool. All right. And of course, what am I checking out? Why do I know that this is a valid probability distribution? Yeah, these add up to 1, check, and,
It's less than 0.
well, thankfully not. All the probabilities are between
1 and 0.
0 and 1. You guys with me? That one seems kind of silly, but you still have to say it. Because they could add up to 1, but one of them could be negative. And that's why they add to 1. And of course you can have a negative probability. That's exceptionally frequent. It's so not going to happen. How do I find the mean?
Multiply it.
I love it. So we went through that whole process last time of why does it work that way, and now we can just do it that way. Now that hopefully we understand why it works that way, I can just multiply x times p of x. The weight times the value. And let me point out one little thing. You see if I want to point it out here yet or not. No, I'll point it out in a second. Oh, before we even do that, some of you guys are already doing it maybe. Can somebody give me a guess what the mean would be around? Where's most of the data? Yeah, so and then there's some, of course, there's some way up here at 9, so I would guess maybe 1.8, just to, because these are going to pull it up a little bit, but that a lot of it is 1. So the mean is going to be a little bit over 1. You guys semi with me on that? Okay, good. Why do you have to be able to do that? Just make sure your answer makes sense. If you get 12, it doesn't make a damn bit of sense. Yeah.
So if there's 0 in that thing, it's okay to leave it out? That's why it's okay.
Oh, if there's a 0 here?
Oh, well, you left out the 4, 5, and 8, and 7.
Because nobody said 4, 5,
And that's
8,
okay.
okay. Yeah, but there certainly could be 0. If I say how many kids do you have, you could have 0 kids. And I don't want to leave that out because that would change the average. Zeros have got to be in there. You with me? So zeros are a valid data point. Anything is a valid data point.
Well, then why are they not there?
Because you have to be in a state. You know, you could argue that you're out of the country, but then how am I talking to you? So, because I'm here. You with me? So I don't think 0 could show up here. How many states have you visited? If you say 0, I'm like, well, you're in one now. Oh, okay, well, I guess one. You with me? But in general, 0 is, you don't throw it out. It's gotta be there, or else the numbers get thrown off, right? These would never add up to 1 if you threw out your zeros. So now you do this, and this should hopefully, some of you guys should realize that you could put L1, L2, and then L3 would be L1 times L2. You guys see how you can use the lists, just in case somebody gives you a long list. You do it really quickly, right? This is not too bad. And when you add those up, add up x p of x. What do you get?
1.7.
1.7? Like that? Not too bad. That's at 1.8. That's pretty close. All right. And here's the really cool thing. Let me see if I can get you guys. There's something called expected value. And expected value really is just another name for the average. Whenever you see a 3-line equals, that's like a definition. Expected value is the average. And the really kick-ass thing there, I don't let you put notes on your formula card, but what are the first 3 letters in the equation for the mean? EXP, expected value. I can't beat that. So this is the mean, is that, right near where we thought it should be, right? Now, how in the world do you calculate the standard deviation? All right, let's talk about that. How did we calculate the standard deviation before? I told you I would never make you do those tables from chapter 3. Well, now you got to do this table. I'm evil. These are not going to be that hard, though. Don't worry. What was this formula for standard deviation before?
X minus square root of n minus 1.
Well, n for the population.
Yeah.
X minus the mean squared, right? Okay, how we do? So I still would have to get, now don't worry, we're going to end up with a much better formula than what I'm starting with. So I've got to tell you where the formula comes from, though. So I still would do this. But the same idea here, I can't just average these numbers up directly, can I? Why not? Why can't I just take the average of these 5 numbers?
Because they are different.
They're different, this is true, but it doesn't take into account how many ones you actually have. I have 65% of my list is 1. And so forth. So I can't just add these up and divide by 5 to get the average. I have to multiply them by their weights, by their percentages. So same thing here, actually. I'd have to multiply each of these by its weight. How are we doing so far? Now again, let me just say this again. You'll never have to use that formula in calculations. There's a much easier formula I'm going to use here in a minute. But that's what it looks like. That's what I call a conceptual formula. You can still see the heart of a standard deviation. What's at the heart of a standard deviation? Distance from the mean. You can see that. You with me? What's missing from the formula? And this is the variance, right? So don't worry about the square root. That'll come in later. But the n, right? Where's the over n? What's underneath any probability? N. Sweet. So it's built in. That over n is built in. It's already a part of the probability, right? What's in the bottom of a probability? The total number. So it's already in here. So I don't need it again. Okay, hopeful. Some of you guys are shaking your head. The rest of you are like, just tell me what the formula I'm going to use. So this, I'm not going to make us do this, but just to get us, just to see where this formula comes from. What do you get when you FOIL this?
Oh.
X squared minus 2x
Yeah, 2 mu x plus mu squared, right? You kind of with me so far? I mean, that's not a big step. It's the most algebra we've seen this semester, right? And what do you get if I start to distribute this? Don't you get x squared p of x? Blah, 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 blah. You with me so far? So I'm going to skip the blah, 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 blah steps. I might make it a bonus question, but remember the mean was sum of x over n, right, and all that kind of stuff. So you can throw that in there, and you can kind of futz things around, and what you actually end up with is this formula here is the same as that formula there. Those are the same. Believe it or not. If you actually do all of the algebra from here down, you get here. Now, I'm hoping you guys do notice it is a little bit easier than that. I don't know if you really trust me in that. You know, like it's the same number of letters, but it is a little bit easier. And the really cool thing is, what do I need to add up? What do I need up here so I can add them up? So like the mean, I need a bunch of xp of x's so I can add them up. What do I need up here that the formula needs? The sum of what? What does the formula need?
X squared.
Yeah, I need to have a bunch of x squared p of x's so I can add them up. So that, I want to see if you guys get this. I'm very hopeful. Do you see how we already have x p of x?
Yeah.
So how would I get x squared p of x? I wouldn't square it, because that would be x squared p squared. I multiply by one more x. Right? So to get x squared p of x, I could do L1 times L3. And this is going to be on the handout I give you, so don't freak out with trying to make sense of this yet. So now I can do this times this. Won't that be x squared p of x? So I get 0.65, 0.84, 0.81, something, 1.08. And then something else. I can't think. You can do it, Jeff. 1.62. Yeah. So then what do you get for that sum? If you add these up, you get the sum of x squared p of x. I'm hoping we're semi-used to this idea. My formula needs this. I'm going to get it right here. I'm going to add those up. What do you get when you add those up? 5? Exactly 5? Cool. 2.7. 5, not that I don't trust you. Yeah, it looks like it's going to come out whole. 5?
5.03.
5.03. And see, that's quick. We already have most everything we need, and you can just do it in your lists to make it quick, right? Multiply L1, L3, you got x squared p of x. Now you can throw that into your formula, 5.03 minus the mean. We already figured out the mean was 1.7. 5.03 minus 1.7 squared. Yes, sir.
How's the average 1.7 when the biggest number is 0.65?
Do it one more time.
How is the average 1.7 when the biggest number is 0.65?
That's not a number. That is a percentage of data points.
Okay.
Here are my data points.
Yeah, I see.
1 is the most, so the mean should be drawn down.
Okay.
Cool. Is that all right? Maybe. I've completely ruined some of your days. I'm sorry. Some of you guys are like, oh God. This is not difficult. It is new to you guys. I can understand that. But it's not entirely new. We've done stuff like this before. 5.03 minus 1.7 squared. Yes, sir.
What did you make x squared p of x equal to?
L1 times L3. Yeah. Let me do this for you. So from there, you can do that and take the square root. Not a big deal. Let me give you this handout so you can kind of see how this really is set up. This, of course, is not my handwriting, so you might be able to tell a little better.
How will you get bx?
Say again.
how would you get the x, if you have the x there?
No. So again, both of these have to be given to you. Either they have to be given to you, or they have to give you a way to get them. Yeah. So I have, I think I've done this before. The door closing. On one side, I have a completely worked out example, so make sure you have two sides. And on the back side, I have, of course, a blank one for you guys to try out. So, do the blank side now. You can work with other people. I'm gonna run and grab that other handout. Try to do the blank side. Use that front side as a reference. And of course, after you do all that work, I'll show you a shortcut to get the answer. So you can check your work.